Hello, and welcome to Velorin Sleepy Space Mysteries. Tonight, we will drift slowly into one of the most peaceful wonders in astronomy. The quiet, distant galaxies scattered across the far reaches of the universe. Far beyond the familiar spiral of the Milky Way, beyond the nearby galaxies that share our cosmic neighborhood, there exist countless islands of stars so distant that their light has been traveling toward us for billions of years. When astronomers observe these remote galaxies, they are not simply looking far into space. They are looking deep into time. Some of the faint glows captured by our telescopes began their journey long before our planet formed, long before the sun began to shine, when the universe itself was still young and learning how to build the structures we see today. These distant galaxies are not just faraway objects. They are ancient messages. Each one carries quiet clues about how stars first ignited, how gravity gathered matter into enormous cosmic cities, and how the universe slowly transformed from a hot, chaotic beginning into the calm and structured cosmos we now inhabit. In a previous Velorin journey, we explored how the cosmic web stretches across unimaginable distances, guiding galaxies along invisible filaments of dark matter. Tonight, we will see how distant galaxies fit into that vast structure, and how they reveal the universe's earliest chapters. But for now, there is nothing you need to do. Let your shoulders relax. Let your breathing slow. Allow your mind to drift gently with the rhythm of the cosmos. And as we continue our journey through these relaxing facts about distant galaxies, take a moment to support the channel by subscribing, liking the video, and ringing the bell if you enjoy these peaceful explorations. You can also let me know in the comments where in the world you are listening from tonight. Now, dim the lights of your thoughts, and let us quietly begin our slow journey toward the most distant galaxies in the universe. Imagine the universe long before our sun existed, before Earth formed, before even the Milky Way had fully grown into the spiral galaxy we know today. The cosmos at that time was a much younger and more restless place. Matter had only recently begun gathering itself into the first large structures. Gas drifted through space in vast clouds, slowly pulled together by the gentle but persistent force of gravity. Over immense stretches of time, those clouds collapsed and condensed, eventually forming the earliest galaxies. These early galaxies were not the graceful spirals and smooth ellipticals we often picture today. Instead, they were small, irregular, and chaotic gatherings of stars and gas, constantly changing as gravity reshaped them. When astronomers observe distant galaxies through powerful telescopes, they are often seeing these early, unfinished systems. The light reaching our instruments today began its journey billions of years ago, when the universe itself was still in its youth. This means distant galaxies act like ancient photographs. They show us what the universe looked like during its early chapters. Nearby galaxies reveal the present stage of cosmic history, but the most distant ones allow us to watch the universe learning how to organize itself for the first time. One of the most noticeable features of distant galaxies is their unusual appearance. Many look clumpy, uneven, or oddly shaped. Instead of the clean spiral arms seen in galaxies like the Milky Way, These early systems often resemble scattered clusters of bright knots. Those bright regions are enormous areas where stars are forming rapidly. In the young universe, galaxies contained vast supplies of cold gas, which is the essential ingredient needed to create new stars. Under gravity, this gas could collapse into dense pockets that ignited bursts of star formation. These regions glowed brightly because massive young stars emit intense energy before ending their short lives in spectacular explosions. Another remarkable characteristic of distant galaxies is their color. Many appear reddish when viewed through telescopes designed to observe extremely remote objects. At first glance, this red glow might seem mysterious, but its explanation lies in the expansion of the universe itself. Space is not static. Since the beginning of cosmic time, space has been slowly stretching. As light travels across the expanding universe, the waves of that light are stretched as well. The longer the journey, the more the light waves expand. Blue or ultraviolet light emitted by young stars billions of years ago gradually shifts toward longer wavelengths, eventually arriving at our telescopes as red or infrared light. This stretching effect is called redshift, and it acts as a kind of cosmic timestamp. The greater the redshift of a galaxy's light, the farther away the galaxy is, and the earlier in the universe's history we are seeing it. Astronomers use redshift measurements to arrange galaxies along a timeline of cosmic evolution. In this way, the night sky becomes a layered archive of the universe's past. But distance does not only reveal youth, it also reveals motion. Because space is expanding, distant galaxies are slowly drifting away from us. The farther a galaxy lies, the faster it appears to recede. This does not mean galaxies are racing through space like rockets. Instead, the space between galaxies is stretching, gently carrying them farther apart over billions of years. These early galaxies were also much more crowded than galaxies today. In the young universe, cosmic structures were packed closer together, and gravitational encounters happened more frequently. Galaxies regularly passed near one another, tugging on each other's gas and stars. Sometimes they merged completely, forming larger galaxies from smaller building blocks. These mergers played an important role in shaping the galaxies we see today. If we could watch the universe in fast motion across billions of years, we would see countless small galaxies drifting together, colliding, and gradually assembling into larger systems. Over time, chaotic clumps of stars slowly settled into more organized forms. Disks began to rotate smoothly, spiral arms appeared, central bulges formed, and the grand galaxies of the modern universe slowly emerged from those early beginnings. For now, though, our story remains in that earlier age, when galaxies were still growing rapidly and the universe itself was filled with energetic change. In the next part of our journey, we will look more closely at how these young galaxies gathered their mass, why collisions were so common, and how gravity slowly transformed cosmic chaos into the ordered galaxy structures we see across the universe today. If we continue drifting backward through time, deeper into the era of distant galaxies, the universe begins to feel less like the calm cosmic landscape we see today and more like a busy construction site. In those early billions of years, galaxies were not yet settled structures. Instead, they were constantly growing, merging, and reshaping themselves under the influence of gravity. Small galaxies formed first, gathering from clouds of hydrogen and helium gas that filled the young cosmos. These small systems were the earliest building blocks, the seeds from which larger galaxies would eventually grow. Gravity slowly pulled nearby clumps of matter toward one another. When two young galaxies drifted close together, their stars rarely collided directly, because the distances between individual stars are enormous. Instead, the gravitational pull between the galaxies stretched their shapes, tugged their gas clouds, and scrambled their internal motions. Long streams of stars could be pulled outward like delicate ribbons, while gas clouds collided and compressed. These compressed clouds often ignited intense bursts of star formation, creating brilliant clusters of young stars that lit up the merging galaxies. This process of merging and gathering was incredibly common in the early universe. Galaxies lived closer together, and their interactions happened frequently over cosmic time. Each encounter slowly built larger and more complex structures. A small galaxy might merge with another small galaxy, forming a slightly larger system. Later, that larger system might merge again, continuing the slow assembly of mass across billions of years. The galaxies we see today are the products of this long sequence of cosmic meetings. Because these early systems were still assembling, many distant galaxies appear fragmented and irregular when observed through powerful telescopes. Some look like scattered islands of light, with bright knots separated by darker regions of gas and dust. These knots are not random patterns. They are enormous star-forming regions, sometimes many times larger than the star-forming complexes found inside nearby galaxies today. In the young universe, galaxies contained far greater supplies of raw gas, and that gas could collapse into massive clusters where stars formed rapidly. Within these bright regions, new stars were born in large numbers. Many of these stars were extremely massive, far larger than our sun. Massive stars burn their fuel quickly and shine intensely, producing powerful ultraviolet radiation that floods their surroundings. Their lifetimes are short by cosmic standards, lasting only a few million years before they explode as supernovae. These explosions send newly forged elements outward into the surrounding gas, enriching the galaxy with heavier atoms that future generations of stars can use. This enrichment process gradually changed the chemical makeup of galaxies over time. In the earliest galaxies, most of the matter consisted of hydrogen and helium, the simplest elements created shortly after the beginning of the universe. Heavier elements like carbon, oxygen, and iron had to be manufactured inside stars and released into space through stellar winds and supernova explosions. Each generation of stars added more complex ingredients to the galactic environment. Over many billions of years, galaxies slowly accumulated the elements necessary to build planets, oceans, and eventually life. But the process of galaxy growth was not always gentle. As galaxies merged, their gas clouds were often thrown into chaotic motion. Streams of gas could rush toward the center of the merging system, piling up into dense regions where new stars formed at extraordinary rates. These episodes are known as starbursts. During a starburst, a galaxy may produce new stars dozens or even hundreds of times faster than it normally would. For a relatively brief period in cosmic history, the galaxy glows with intense activity before the available gas is gradually used up or blown away by stellar explosions. These energetic events also stirred the structure of young galaxies. Instead of calm, rotating disks, many early galaxies looked thick, turbulent, and unstable. Massive clumps of stars could migrate inward toward the center of the galaxy, eventually helping to form the dense central regions seen in many mature galaxies today. Over time, gravity slowly smoothed out these chaotic beginnings. Gas settled into rotating disks, stars spread into more stable orbits, and the familiar spiral patterns began to emerge. Yet, even while this gradual order was forming, the universe remained filled with restless motion. Galaxies continued drifting toward one another along vast, invisible pathways shaped by gravity. Some would merge completely, becoming larger galaxies. Others would pass close enough to exchange streams of gas and stars before drifting apart again. These interactions created an evolving cosmic landscape where galaxies constantly influenced one another's growth. And as we continue exploring these distant galaxies, another mystery begins to emerge quietly in the background of this story. Much of the gravity shaping these galaxies does not appear to come from the stars we can see. Instead, astronomers have discovered that an unseen form of matter surrounds galaxies, guiding their formation and influencing their motion across the universe. In the next part of our journey, we will begin to explore this hidden architecture of the cosmos and how invisible structures helped shape the distant galaxies we observe today. As astronomers continued studying distant galaxies, another quiet mystery began to reveal itself. When researchers carefully measured how stars moved inside galaxies, they noticed something unexpected. The visible stars and gas did not seem to provide enough gravity to explain the motions they observed. In many galaxies, stars near the outer edges were moving far faster than expected, almost as if an invisible mass were holding the entire structure together. This led to the discovery that galaxies appear to be surrounded by enormous halos of unseen matter. This mysterious substance does not shine, reflect light, or absorb radiation in ways our telescopes can easily detect. Yet its gravitational influence is unmistakable. Astronomers call this hidden substance dark matter, and it seems to make up the majority of the mass within most galaxies. Although dark matter cannot be directly observed, its presence becomes clear through its effects on the motion of stars and gas. When astronomers map the rotation of a galaxy, they expect orbital speeds to slow down farther from the center, much like planets in our solar system move more slowly when they are farther from the sun. Instead, many galaxies show a surprising pattern. Their outer stars continue orbiting at high speeds, as if a massive halo of invisible material extends far beyond the visible galaxy. This discovery revealed that galaxies are not simply islands of stars floating through space. Instead, they are embedded inside enormous halos of dark matter that stretch far beyond the glowing regions we can see. These halos act like invisible scaffolding for the universe. Long before stars formed, dark matter gathered into large clumps under the pull of gravity. Ordinary matter, made of gas and atoms, then fell into these clumps, eventually forming the first galaxies. In this way, dark matter played a crucial role in shaping the structure of the universe. Without its gravitational influence, gas might have remained too spread out to collapse into stars and galaxies. Instead, dark matter created gravitational wells where matter could gather more efficiently. Galaxies formed at the centers of these wells, gradually growing as more gas and smaller galaxies drifted inward. These dark matter halos are not isolated structures. They connect to one another across vast distances, forming an enormous network known as the cosmic web. On the largest scales, the universe resembles a vast three-dimensional network of filaments and nodes. Along these filaments, galaxies and galaxy clusters are strung together like glowing beads on invisible threads. Between the filaments lie enormous voids where very few galaxies exist. Distant galaxies often appear along these cosmic filaments because gravity slowly pulls matter toward these preferred pathways. Gas flows along the filaments toward dense regions where galaxies are already forming. This steady supply of material feeds star formation and allows galaxies to grow over time. The cosmic web therefore acts like a network of intergalactic highways, guiding matter across enormous distances. When astronomers map the positions of millions of galaxies across the sky, this web-like structure becomes strikingly clear. Large clusters of galaxies form where multiple filaments intersect, creating enormous cosmic cities filled with hundreds or even thousands of galaxies. In contrast, the vast spaces between these filaments contain very little matter at all. Within these crowded environments, galaxies continue interacting with one another. Some fall into clusters and experience dramatic changes as they move through dense regions filled with hot gas and powerful gravitational forces. Others remain along quieter filaments where they evolve more slowly. The environment surrounding a galaxy can strongly influence how it grows, how many stars it forms, and whether it continues forming stars at all. Yet even with this hidden architecture guiding their formation, galaxies remain dynamic and evolving systems. Gas flows inward along cosmic filaments, feeding new generations of stars. Supernova explosions push material outward, stirring the gas and spreading heavier elements across the galaxy. Black holes at galactic centers sometimes awaken, releasing enormous energy that can shape the surrounding environment. All of these processes occur simultaneously, creating the complex and ever-changing galaxies we observe today. Distant galaxies therefore reveal not just the early universe, but also the hidden forces shaping cosmic evolution. And as astronomers peer deeper into space with increasingly powerful telescopes, another fascinating phenomenon begins to appear. In some cases, the gravity of massive galaxies and galaxy clusters bends the light from even more distant galaxies behind them. This bending of light can stretch distant galaxies into arcs or rings, sometimes magnifying their brightness and allowing astronomers to study objects that would otherwise remain far too faint to detect. In the next part of our journey, we will explore this strange effect of gravity bending light and how the universe itself sometimes acts like a giant natural telescope, revealing distant galaxies that would otherwise remain hidden in the darkness of deep space. As telescopes began observing deeper into space, astronomers discovered something both beautiful and strange. Some distant galaxies did not appear as simple points of light or faint smudges. Instead, they appeared stretched into long arcs, curved streaks, or even glowing rings. At first glance, these shapes seemed unusual, almost like distorted reflections in a cosmic mirror. But these shapes were not accidents or flaws in the images. They were evidence that gravity itself can bend the path of light traveling across the universe. This phenomenon is known as gravitational lensing. It happens when a massive object, such as a galaxy or a cluster of galaxies, lies directly between us and a more distant galaxy far behind it. The gravity of the foreground object curves the surrounding fabric of space. When light from the distant galaxy travels through that curved region of space, its path is bent, just as light bends when it passes through a glass lens. The result is that the distant galaxy can appear stretched, magnified, or split into multiple images. Sometimes the alignment between the foreground mass and the distant galaxy is nearly perfect. When this happens, the light can wrap around the gravitational lens and form a nearly complete circle of light known as an Einstein ring. These glowing rings are rare but breathtaking examples of gravity shaping the appearance of the cosmos. More commonly, astronomers observe long curved arcs surrounding massive galaxy clusters, each arc representing the distorted image of a galaxy lying far behind the cluster. Gravitational lensing is more than just a visual curiosity. It has become one of the most powerful tools astronomers use to study distant galaxies. Many of the earliest galaxies in the universe are extremely faint. Their light has traveled for billions of years and spread across enormous distances, making them difficult to detect even with the most advanced telescopes. But when a massive cluster sits between us and those distant galaxies, the cluster's gravity can magnify the background light, effectively acting like a natural telescope. This cosmic magnification allows astronomers to study galaxies that would otherwise remain invisible. Features that would normally appear as tiny points can be stretched and brightened enough to reveal structure. Scientists can measure the chemical composition of their gas, estimate how rapidly they are forming stars, and even observe how matter moves within them. In this way, gravity itself becomes an instrument that helps extend our vision deeper into the universe. Gravitational lensing also reveals something else important about the cosmos. By carefully measuring the way distant galaxies are distorted, astronomers can map the distribution of mass within the lensing object. When they perform these measurements, they often find that the visible galaxies within a cluster account for only a small fraction of the mass required to produce the observed lensing effects. The rest of the mass appears to come from the invisible dark matter halos surrounding the cluster. This makes gravitational lensing one of the most convincing pieces of evidence that dark matter truly exists. Unlike measurements of galaxy rotation, which rely on the motion of stars, lensing measures the bending of light directly. Gravity bends light regardless of whether the mass causing the bending is visible or invisible. By studying these distortions, astronomers can effectively weigh cosmic structures that they cannot see. Sometimes lensing produces another remarkable effect. A single distant galaxy may appear as multiple images arranged around the foreground object. Each image represents light that traveled along a slightly different path through curved space. Because those paths have slightly different lengths, the light from each image can arrive at Earth at slightly different times. If the distant galaxy suddenly brightens, astronomers might observe the brightening in one image first, then later in another image as the delayed light arrives. This strange phenomenon means that gravitational lensing can even turn the universe into a kind of natural time experiment. Astronomers can measure these time delays and use them to study the expansion rate of the universe itself. The geometry of space, the distribution of mass, and the stretching of cosmic distances all influence how long each light path takes to reach us. Meanwhile, behind these natural gravitational lenses, the distant galaxies continue shining across the depths of time. Their light carries information about an era when galaxies were still assembling and the universe itself was much younger. Some appear as small, compact bursts of star formation. Others already show signs of structure beginning to organize within them. Each one represents a tiny window into a moment billions of years in the past. In the final part of this section, we will explore how some distant galaxies shine so brightly that they outshine entire galaxies of stars, and how enormous black holes at their centers can transform a galaxy into one of the most luminous beacons in the universe. Among the countless distant galaxies scattered across the early universe, some shine with an intensity that seems almost impossible. When astronomers first detected these brilliant points of light decades ago, they appeared almost like ordinary stars in the night sky. Yet when their distances were measured, a surprising truth emerged. These objects were not nearby stars at all. They were galaxies located billions of light years away, and somehow they were producing more light than entire galaxies filled with hundreds of billions of stars. The explanation for this extraordinary brightness lies deep within the centers of many galaxies. At the heart of most galaxies sits a supermassive black hole, an object whose gravity is so strong that nothing can escape once it crosses the boundary known as the event horizon. On its own, a black hole is completely dark. Yet the environment around it can become one of the most energetic places in the universe. When gas and dust drift toward a supermassive black hole, they rarely fall directly inward. Instead, the material forms a rapidly spinning disk around the black hole. As the gas spirals closer, friction and compression heat the material to extreme temperatures. This glowing whirlpool of matter, called an accretion disk, can radiate enormous amounts of energy across the electromagnetic spectrum. In some cases, the light from this compact region can outshine the combined starlight of the entire galaxy surrounding it. These extraordinarily bright galactic cores are known as quasars. During the early universe, quasars were far more common than they are today. Many young galaxies contained large supplies of gas falling toward their central black holes, fueling these brilliant cosmic beacons. Because quasars are so luminous, they can be seen across enormous distances, making them valuable tools for studying the distant universe. Quasars also act like powerful backlights shining through the cosmic landscape. As their light travels across billions of light-years, it passes through the thin gas that exists between galaxies. That gas absorbs very specific wavelengths of light, leaving delicate patterns of absorption lines in the quasar spectrum. By studying these patterns, astronomers can detect clouds of gas that would otherwise be completely invisible. Each tiny absorption feature reveals the presence of hydrogen or other elements floating in intergalactic space. By analyzing how these features change with distance, astronomers can reconstruct a map of matter spread across enormous regions of the universe. In this way, quasars allow scientists to explore the invisible material that fills the vast spaces between galaxies. Some active galaxies also produce another extraordinary phenomenon. In certain cases, the region near the black hole launches narrow jets of energetic particles that travel outward at speeds close to that of light. These jets can extend far beyond the galaxy itself, sometimes stretching for hundreds of thousands or even millions of light-years into intergalactic space. As the particles spiral around magnetic fields within the jets, they emit a special kind of radiation known as synchrotron radiation, which glows strongly in radio wavelengths. At the far ends of these jets, enormous lobes of energized gas can form, creating structures far larger than the host galaxy. Even though the stars within the galaxy may appear calm and stable, the presence of these jets reveals that powerful processes are unfolding near the galactic center. The energy released by the black hole can influence the entire galaxy, heating surrounding gas and sometimes slowing the formation of new stars. This connection between black holes and galaxy evolution is one of the most fascinating discoveries in modern astronomy. It appears that the growth of supermassive black holes and the growth of galaxies themselves are closely linked. When galaxies gather gas to form new stars, some of that material may also drift inward toward the central black hole. When the black hole becomes active, the energy it releases can push gas outward, temporarily slowing star formation. In this way, galaxies and their central black holes evolve together, shaping each other's history over billions of years. As we conclude this chapter of our journey through distant galaxies, we begin to see the young universe as a place filled with intense activity. Galaxies were colliding and merging, massive stars were forming and exploding, and enormous black holes were lighting up the centers of galaxies with incredible brilliance. Yet even within this energetic environment, gravity continued its slow work of organizing matter into the large structures we observe today. In the next part of our cosmic exploration, we will move beyond the early growth of galaxies and begin to explore the vast environments in which they live. We will drift through galaxy groups and clusters, trace the enormous cosmic web connecting galaxies across unimaginable distances, and uncover how the largest structures in the universe shape the lives of galaxies over billions of years. When we look at distant galaxies, it is easy to imagine them as isolated islands of stars drifting quietly through the darkness of space. But the deeper astronomers look into the universe, the more they realize that galaxies rarely exist alone. Instead, most galaxies live in communities, influenced by their neighbors and shaped by the gravitational environment surrounding them. These cosmic neighborhoods range from small groups containing only a handful of galaxies to enormous clusters holding thousands of members, all bound together by gravity across millions of light years. Our own Milky Way is part of such a neighborhood. It belongs to a modest gathering called the Local Group, which includes several dozen galaxies of various sizes. The Milky Way and the nearby Andromeda Galaxy are the largest members, surrounded by smaller dwarf galaxies that orbit them like quiet companions. These small systems may seem insignificant compared to their larger neighbors, yet they play an important role in the story of galaxy evolution. Dwarf galaxies are often considered the building blocks of larger galaxies. In the early universe, many galaxies were small and irregular. Over billions of years, larger galaxies grew partly by absorbing these smaller systems. When a dwarf galaxy drifts too close to a massive neighbor, gravity begins to stretch it. Stars can be pulled away from the dwarf, forming long, faint streams that wrap around the larger galaxy like delicate ribbons of light. These stellar streams are not merely beautiful structures. They are clues about past encounters. By tracing the paths of these streams, astronomers can reconstruct the orbits of the captured galaxies and learn how larger galaxies gradually assembled their mass. In many ways, the outer halos of galaxies act like historical records, preserving evidence of ancient mergers that occurred billions of years ago. Galaxy groups provide an environment where these interactions happen frequently but slowly. Galaxies within a group orbit around their shared center of gravity for billions of years, occasionally passing close enough to influence one another. These encounters can tug on gas clouds, distort spiral arms, and sometimes trigger bursts of star formation. Even without direct collisions, the steady gravitational pull between neighboring galaxies can reshape their structures over time. In some cases, two galaxies gradually spiral toward each other and merge completely. When this happens, their stars mix together while their gas clouds collide and compress. The result can be a dramatic increase in star formation, creating bright clusters of young stars that illuminate the merging system. Over time, the chaotic motions settle, leaving behind a larger galaxy with a new shape. While galaxy groups represent relatively quiet neighborhoods, galaxy clusters are the crowded cities of the cosmos. These massive structures can contain hundreds or even thousands of galaxies bound together by an immense gravitational field. The space within a cluster is filled not only with galaxies but also with vast reservoirs of extremely hot gas that glow in X-ray light. This gas is heated to tens of millions of degrees by the cluster's deep gravitational well. Galaxies moving through this environment travel at extraordinary speeds, often thousands of kilometers per second. As they plunge through the hot gas between cluster members, they experience a kind of cosmic wind that can strip away their own gas clouds. Without this gas, the galaxies lose the raw material needed to form new stars. Over time, many cluster galaxies become dominated by older, reddish stars as star formation gradually fades. Clusters therefore act as powerful environments for galaxy transformation. A galaxy that enters a cluster may begin its life as a vibrant spiral rich with gas and young stars. But after billions of years moving through the dense cluster environment, it may emerge as a smoother, quieter galaxy with little remaining star formation. the surrounding environment slowly reshapes its future. Despite their enormous scale, galaxy clusters are not the largest structures in the universe. Clusters themselves are connected to one another through the vast filaments of the cosmic web we encountered earlier. These filaments form the skeleton of the large-scale universe, guiding the motion of galaxies and clusters alike. Matter flows slowly along these invisible pathways, feeding clusters and shaping the distribution of galaxies across billions of light-years. In the next stage of our journey, we will travel along these immense cosmic filaments and explore the strange contrast between the crowded galaxy clusters and the vast empty regions known as cosmic voids. These enormous quiet spaces reveal yet another side of the universe's structure, showing how gravity and expansion together sculpt the grand architecture of the cosmos. If galaxy clusters are the crowded cities of the universe, then the spaces between them can feel astonishingly empty. When astronomers map the large-scale structure of the cosmos, they discover a striking pattern. Galaxies are not scattered randomly across space. Instead, they gather along enormous filaments that stretch across hundreds of millions of light-years, forming the vast network known as the cosmic web. Between these filaments lie enormous regions where very few galaxies exist at all. These regions are known as cosmic voids. Cosmic voids are among the largest structures in the universe. Some stretch for tens or even hundreds of millions of light-years, containing only a handful of faint galaxies drifting through immense expanses of nearly empty space. Compared to the dense clusters where thousands of galaxies crowd together, voids can feel like the quiet countryside between bustling cities. Yet these seemingly empty regions play an important role in shaping the universe's overall structure. The existence of voids comes from the same process that formed clusters and filaments. In the earliest moments after the universe began expanding, matter was not distributed perfectly evenly. Tiny differences in density existed throughout space. Some regions contained slightly more matter than others. Over billions of years, gravity amplified these small differences. Regions that were slightly denser pulled in more matter, gradually growing into the filaments and clusters we see today. Meanwhile, the regions that started with less matter slowly lost even more as surrounding material flowed toward the denser areas. These underdense regions expanded and emptied, becoming the cosmic voids. When astronomers survey millions of galaxies across the sky, this pattern becomes remarkably clear. Galaxies line up along enormous strands, connecting clusters like glowing bridges of starlight. At the intersections of these strands, clusters grow especially large because they collect matter flowing from several directions at once. Between these intersections lie the wide, quiet voids where gravity has pulled most matter away. Although voids contain far fewer galaxies, they are not completely empty. A small number of galaxies can still form there, usually smaller and more isolated systems. Because these galaxies experience fewer gravitational encounters with neighbors, they often evolve more slowly than galaxies in crowded environments. Without frequent mergers or strong gravitational disturbances, some void galaxies maintain their gas reservoirs for longer periods of time, quietly forming stars over extended cosmic timescales. Meanwhile, galaxies located along filaments experience a very different environment. Gas flows along these cosmic strands, gradually feeding galaxies with fresh material. This inflow of gas helps sustain star formation and allows galaxies to grow steadily. Over time, smaller galaxies drifting along a filament may move toward larger structures at the filament's intersections, eventually becoming part of galaxy groups or clusters. This slow movement of matter across the cosmic web means that galaxies are never completely isolated from their surroundings. Even when they appear alone, they are often connected through vast gravitational structures stretching across unimaginable distances. The cosmic web therefore acts as the underlying architecture of the universe, guiding where galaxies form and how they evolve over time. Astronomers study this structure by measuring the positions and distances of millions of galaxies. By combining these measurements into three-dimensional maps, they can visualize the large-scale arrangement of matter across enormous volumes of space. The resulting maps reveal a universe that looks surprisingly organic, with filaments, nodes, and voids forming patterns that resemble a delicate network. Yet even with this grand structure mapped out, many mysteries remain. One of the most intriguing questions concerns the role of dark matter in shaping these cosmic patterns. Since dark matter provides most of the gravitational pull in the universe, it largely determines how matter flows into filaments and clusters. Computer simulations suggest that the cosmic web first formed in dark matter long before galaxies appeared. Ordinary matter then followed this invisible framework, eventually forming stars and galaxies along the same pathways. This means the luminous galaxies we observe today may simply be tracing the outlines of a much larger and mostly invisible structure built from dark matter. In other words, the glowing galaxies we see are like lanterns hung along the beams of a vast cosmic scaffold. As our journey continues, we will begin to look more closely at how galaxies themselves change over time within this enormous structure. Some galaxies continue forming stars for billions of years, while others gradually stop producing new stars altogether. In the next part of our exploration, we will discover why some galaxies remain vibrant and active, while others slowly fade into quieter stages of their cosmic lives. As galaxies travel through the vast structure of the cosmic web, their lives slowly change. Some galaxies remain rich with cold gas and continue forming new stars for billions of years. Others gradually lose their ability to create new stars and enter a quieter stage of existence. Astronomers often describe these two broad types as star-forming galaxies and quenched galaxies. Understanding why galaxies fall into one category or the other has become one of the central questions in the study of galaxy evolution. A galaxy's color offers one of the simplest clues about its activity. Galaxies that are actively forming stars often appear bluish when viewed through telescopes. This color comes from massive young stars that burn extremely hot and emit large amounts of energetic light. These stars do not live long. Many of them shine brightly for only a few million years before exploding as supernovae. Because they are short-lived, their presence indicates that star formation is happening right now or has happened very recently. Galaxies that appear red tell a different story. In these systems, the bright blue stars have already lived out their short lives and disappeared. What remains are longer-lived stars that shine with cooler, redder light. These stars can survive for billions of years, slowly aging while the galaxy around them grows quieter. When astronomers see a galaxy dominated by reddish light, it often means that star formation has slowed dramatically or stopped altogether. But what causes a galaxy to stop forming stars? One reason can be the loss of cold gas, which is the raw material needed to build new stars. In crowded environments like galaxy clusters, galaxies moving through hot intergalactic gas can have their own gas stripped away. As a galaxy plunges through the cluster, pressure from the surrounding gas acts like a powerful wind, sweeping away the galaxy's star-forming fuel. Without that fuel, star formation gradually fades. Another process that can influence star formation occurs deep within a galaxy's core. At the center of most galaxies lies a supermassive black hole. When large amounts of gas fall toward this black hole, the surrounding region can release enormous energy. Some of that energy can heat nearby gas or push it outward into space. If the gas becomes too hot or too dispersed, it cannot collapse into dense clouds where stars are born. In this way, the activity of a galaxy's central black hole can regulate how many new stars the galaxy produces. There are also internal processes that shape a galaxy's future. Within spiral galaxies, long structures called bars can form across the central region. These bars act like slow-moving conveyor belts, guiding gas from the outer regions toward the galaxy's center. As the gas flows inward, it can accumulate in dense rings or central reservoirs where bursts of star formation occur. Over time, however, this inward flow can also deplete the gas available in the outer disk, gradually changing the galaxy's structure. Galactic collisions can also transform a galaxy's ability to form stars. When two galaxies merge, their gas clouds collide and compress, often triggering intense starbursts. For a brief cosmic moment, the merging system may form stars at extraordinary rates. But this burst of activity consumes large amounts of gas in a relatively short time. Once the gas supply is exhausted or heated by stellar explosions, star formation slows again. Over billions of years, these different processes gradually shift galaxies along a broad evolutionary path. A young galaxy may begin as a turbulent system rich with gas and active star formation. As time passes and interactions reshape its structure, the galaxy may lose gas, use up its fuel, or have its gas heated by energetic processes. Eventually, it may settle into a quieter stage where its existing stars continue shining, but few new stars are born. Yet even when star formation slows, galaxies continue evolving in other ways. Large galaxies can still grow by absorbing smaller companions. This process, sometimes called galactic cannibalism, occurs when a massive galaxy gradually pulls smaller neighbors toward itself through gravity. Over time, the smaller galaxies are torn apart, their stars spreading into faint halos around the larger galaxy. These outer halos often contain delicate streams, shells, and arcs made from the stars of captured galaxies. Deep observations of nearby galaxies reveal these structures as faint glowing traces surrounding the main body. Each stream represents a memory of a past encounter, preserving evidence of how galaxies assembled their mass over time. As astronomers study these structures more closely, they are learning that the history of a galaxy is rarely simple. Even galaxies that appear calm and symmetrical today may carry hidden evidence of dramatic events that happened billions of years ago. Their smooth shapes may conceal ancient mergers, gravitational encounters, and long periods of gradual transformation. In the next part of our journey, we will explore some of the surprising shapes galaxies can take as a result of these encounters. From enormous tidal tails stretching across space to unusual rings and tilted structures, the universe reveals that gravity is capable of sculpting galaxies into a remarkable variety of forms. When galaxies interact with one another, gravity can sculpt them into shapes that stretch far beyond their original boundaries. These encounters do not happen quickly by human standards. Instead, they unfold slowly over hundreds of millions or even billions of years. Yet, despite this slow pace, the effects can be dramatic. Entire rivers of stars can be pulled outward, forming enormous structures known as tidal tails. These delicate streams of light can extend hundreds of thousands of light years into space, arching gracefully away from the galaxies that created them. Tidal tails form when two galaxies pass close enough for their gravitational forces to strongly influence each other. The outer stars and gas in each galaxy are only loosely bound, and during a close encounter gravity can stretch these outer regions like soft taffy. As the galaxies move past each other, long arcs of stars are drawn outward, tracing the invisible paths of gravitational forces at work. In some systems, two sweeping tails appear on opposite sides of the interacting galaxies, each one marking a different direction in which matter was pulled away. These tails are not just temporary decorations. In many cases, they remain visible for hundreds of millions of years, slowly dispersing as their stars continue orbiting within the larger gravitational field. Astronomers study these structures carefully because their shapes contain clues about the galaxies that produced them. By recreating these interactions in computer simulations, scientists can estimate how close the galaxies passed, how massive they were, and how their original orientations influenced the encounter. Sometimes the material inside tidal tails can gather into new structures of its own. Gas and stars pulled out during a galactic interaction may clump together under gravity, forming small self-contained systems known as tidal dwarf galaxies. These newborn galaxies are unusual because they are made from recycled material that once belonged to larger galaxies. As a result, they often contain higher amounts of heavy elements than ordinary dwarf galaxies that formed earlier in cosmic history. In this way, galaxy interactions do not only destroy structures, they can also create new ones. Other encounters can produce different patterns entirely. In certain cases, when a smaller galaxy plunges through the disk of a larger one, it sends a ripple traveling outward through the larger galaxy's stars and gas. The ripple compresses gas as it moves, triggering waves of star formation along its path. The result can be a glowing circular ring expanding outward from the center, sometimes resembling ripples spreading across the surface of a pond after a stone is dropped into the water. These ring galaxies provide a striking example of how a single gravitational event can reshape an entire galaxy. There are also galaxies that display even stranger geometries. Some systems contain rings of stars and gas orbiting at steep angles compared to the main disk of the galaxy. These unusual structures are known as polar ring galaxies. In such systems, a secondary ring or disk circles the galaxy almost perpendicular to its primary disk, giving the appearance of one galaxy wearing another galaxy's belt. Astronomers believe these structures form when a galaxy captures gas from a passing neighbor or absorbs material from a smaller companion whose orbit was tilted relative to the main disk. Because these polar rings move in such unusual orientations, they provide valuable clues about the distribution of mass within the galaxy. The ring's orbit responds to the galaxy's overall gravitational field, including the extended halo of dark matter surrounding it. By studying the motion of stars and gas in the ring, astronomers can infer how the galaxy's mass is distributed far beyond the visible stars. Not all galaxies display dramatic features like tails or rings. Some appear remarkably smooth and quiet, with very little visible structure. These galaxies often contain mostly older stars and very little cold gas. Without abundant gas, spiral arms may fade or fail to form altogether. In the next part of our journey, we will begin exploring how astronomers use powerful telescopes to uncover these distant galaxies and piece together their histories. From the famous deep-field images that revealed thousands of galaxies in tiny patches of sky to the newest infrared observatories capable of detecting some of the earliest galaxies ever formed, our view of the universe continues to deepen with every generation of instruments. As astronomers continued studying galaxies across larger and larger regions of the sky, they began to realize something remarkable. The universe was far more crowded than it appeared to the human eye. When we look up at the night sky without telescopes, we see only a few thousand stars and perhaps the faint band of the Milky Way stretching across the darkness. Yet when powerful telescopes observe even a tiny patch of sky for long periods of time, an astonishing truth appears. What once looked like empty darkness is often filled with countless distant galaxies. One of the most famous examples of this discovery came from an observation known as the Deep Field Experiment. Astronomers pointed a space telescope toward a very small region of the sky that appeared almost completely empty. The patch of sky they selected was so tiny that it would fit within the width of a grain of sand held at arm's length. For several days, the telescope collected faint light from that single region, patiently gathering photons that had been traveling across space for billions of years. When the final image was assembled, the results surprised even many astronomers. Instead of darkness, the image revealed thousands of galaxies packed into that tiny portion of the sky. Some were relatively nearby and displayed recognizable spiral structures. Others were small reddish smudges whose light had begun its journey when the universe was far younger. The experiment demonstrated something profound. The universe is not sparsely populated with galaxies. Instead, galaxies fill space in almost every direction we look. This realization changed how scientists think about the cosmos. If such a tiny region of sky contains thousands of galaxies, then the observable universe must contain hundreds of billions of them. Each of these galaxies carries its own history of star formation, collisions, and evolution. The sky we see above us is therefore not just a collection of distant lights. It is a vast map of other cosmic worlds, each one evolving across immense stretches of time. As telescope technology improved, astronomers pushed this method even further. By allowing telescopes to observe a region of sky for longer periods, they were able to detect even fainter galaxies. These deeper observations revealed objects so distant that their light had been stretched far beyond visible wavelengths by the expansion of the universe. Many of these ancient galaxies appeared as faint reddish glows, hinting at the earliest stages of galaxy formation. To observe these extremely distant objects, astronomers began building telescopes designed to detect infrared light. Infrared wavelengths are longer than the visible light our eyes can see. Because light from very distant galaxies is stretched during its journey through expanding space, it often arrives at Earth in the infrared portion of the spectrum. By observing these wavelengths, astronomers can detect galaxies that would otherwise remain invisible. Infrared observations have revealed galaxies forming when the universe was only a small fraction of its current age. Some of these early systems appear compact and intensely bright, filled with rapid star formation. Others show surprising levels of structure, suggesting that galaxies may have organized themselves more quickly than scientists once expected. These discoveries have led to new questions about how galaxies assembled in the early universe. Did some galaxies grow extremely fast, gathering mass more rapidly than current models predict? Or do the observations reveal structures that appear larger because of gravitational lensing or other observational effects? Astronomers continue testing these ideas by combining observations from multiple telescopes and comparing the results with detailed computer simulations. At the same time, the increasing sensitivity of modern instruments has allowed astronomers to analyze the light from distant galaxies in greater detail. By splitting this light into spectra, scientists can identify the chemical elements present in these early systems. Each element leaves a distinct signature in the light it emits or absorbs. By studying these patterns, astronomers can determine how enriched a galaxy's gas has become with heavier elements created by earlier generations of stars. These measurements help reveal how galaxies gradually built the chemical ingredients needed for planets and complex chemistry. Early galaxies contained mostly hydrogen and helium, but over time the cycles of star formation and stellar explosions produced heavier elements such as carbon, oxygen, and iron. Each new generation of stars enriched the surrounding gas, allowing future stars and planetary systems to form from more complex materials. As this long story unfolds across cosmic time, distant galaxies act like pages in a vast archive of the universe's past. Each one preserves information about a particular moment in cosmic history. By comparing galaxies at different distances, astronomers can piece together how galaxies grew, changed shape, and gradually assembled the structures we observe today. And yet, even with all these discoveries, the universe still holds countless secrets waiting to be revealed. In the next stage of our journey, we will explore how modern telescopes are now peering even deeper into the early universe than ever before, revealing galaxies that formed not long after the first stars began to shine. For most of human history, the distant galaxies of the universe were completely hidden from view. The stars we could see with our eyes belonged almost entirely to our own galaxy, the Milky Way. Even the nearest galaxies appeared only as faint cloudy patches through early telescopes. It was not until the 20th century that astronomers began to understand just how vast and populated the universe truly is. As telescope technology improved, scientists gained the ability to collect more light from extremely faint objects. Light from distant galaxies arrives at Earth as only a tiny trickle of photons that have traveled for billions of years. Each photon carries a small piece of information about its source. By gathering many of these photons over long periods of time, astronomers can slowly build an image of galaxies that would otherwise remain invisible. Long exposures became one of the most powerful techniques in astronomy. Instead of taking a single short picture of the sky, telescopes observed the same region for hours, days, or even weeks. During that time, faint light from distant galaxies gradually accumulates on sensitive detectors. The process is somewhat like filling a cup with slow droplets of rain. One drop alone might seem insignificant, but with patience the cup eventually fills. When astronomers combine these long exposures, incredibly faint galaxies begin to appear. Objects that once looked like empty darkness reveal subtle shapes and delicate smudges of light. Some of these galaxies are so distant that their light began traveling toward us when the universe was still very young. In this way, powerful telescopes allow astronomers to look farther back into cosmic history than ever before. One important challenge when observing extremely distant galaxies is the stretching of light caused by the expansion of the universe. As we explored earlier, the light emitted by ancient galaxies becomes redshifted during its journey through expanding space. Wavelengths that were originally emitted as ultraviolet or visible light are gradually stretched into infrared wavelengths by the time they reach Earth. For this reason, many modern telescopes are designed to detect infrared light with exceptional sensitivity. Infrared detectors can capture the faint glow of ancient stars whose light has traveled for more than 10 billion years. Without these instruments, many of the earliest galaxies would remain completely invisible to us. Another challenge arises from the presence of dust inside galaxies. Dust grains are extremely effective at absorbing visible and ultraviolet light. In many galaxies, especially those undergoing intense star formation, dust clouds can hide large regions of activity from ordinary telescopes. However, dust behaves differently at longer wavelengths. After absorbing energetic light from young stars, dust warms slightly and re-emits that energy as infrared radiation. This means that infrared telescopes can often see galaxies that appear dim or hidden in visible light. Instead of observing the starlight directly, astronomers detect the warm glow of dust heated by star formation. In this way, infrared observations reveal parts of the universe that were previously concealed behind cosmic curtains. By combining observations from multiple wavelengths, visible, infrared, radio, and X-ray, astronomers can build a much more complete picture of distant galaxies. Each wavelength reveals a different part of the story. Visible light shows the stars themselves. Infrared light traces warm dust and hidden star formation. Radio observations reveal cold gas that may eventually form new stars. X-rays highlight extremely energetic environments such as hot gas and active black holes. When these different views are layered together, distant galaxies become far more than faint points of light. They become complex systems with structure, chemistry, and motion that can be studied in remarkable detail. And as telescope technology continues advancing, astronomers are now beginning to detect galaxies that formed closer and closer to the very beginning of cosmic history. In the next stage of our journey, we will explore how new observatories are pushing the boundaries of observation even further, revealing galaxies that may have formed only a few 100 million years after the universe itself began. As astronomers continued pushing their instruments to greater sensitivity, a new realization slowly emerged. The earliest galaxies were not only distant and faint, they were also profoundly different from the galaxies we see nearby today. When we look deep into the universe, we are observing galaxies at a time when the cosmos itself was still in the process of organizing its first large structures. In those distant epochs, galaxies were smaller, less chemically enriched, and often far more energetic than many modern systems. One reason early galaxies looked so different is that the universe itself contained fewer heavy elements at that time. In the beginning, almost all matter consisted of hydrogen and helium. The simplest atoms formed shortly after the universe began expanding. The heavier elements needed for rocky planets, complex molecules, and even dust grains had not yet been widely created. Those elements had to be forged inside stars through nuclear fusion and then scattered into space through stellar winds and supernova explosions. Because of this, the earliest galaxies were chemically simple environments. Their gas clouds contained very little carbon, oxygen, silicon, or iron compared with the galaxies we observe nearby. Astronomers often describe these early systems as metal poor, using the astronomical term for elements heavier than helium. This difference in composition affected how gas cooled, collapsed, and formed new stars. Gas containing heavier elements can cool more efficiently because those elements radiate energy as they interact with surrounding particles. Cooling allows gas clouds to condense into smaller, denser regions where stars can form more easily. In the earliest galaxies, however, the lack of heavy elements meant that gas behaved somewhat differently. Clouds often remained warmer and more massive before collapsing, which may have led to the formation of unusually large stars during the universe's earliest epochs. These early generations of stars played a crucial role in transforming their host galaxies. Massive stars burn through their nuclear fuel quickly, producing enormous amounts of energy and ending their lives as powerful supernova explosions. Each explosion spreads newly created elements into the surrounding gas, gradually enriching the galaxy with heavier materials. Over time, these processes changed the chemical composition of galaxies, making later generations of stars and planetary systems possible. Astronomers detect these chemical differences by studying the spectra of distant galaxies. When light from a galaxy is split into its component colors, certain wavelengths appear brighter or darker depending on which elements are present. Each element produces a unique pattern of spectral lines, allowing scientists to identify the ingredients within a galaxy's gas clouds. By measuring how strong these spectral features are, astronomers can estimate the abundance of various elements and learn how chemically evolved a galaxy has become. This technique reveals that galaxies gradually grow richer in heavy elements as cosmic time passes. Younger galaxies from the distant universe often show weaker signatures of metals compared with nearby galaxies that have experienced billions of years of stellar recycling. In this way, the chemical fingerprints of galaxies provide a kind of cosmic timeline, recording the gradual enrichment of matter across the universe. But the earliest galaxies influenced the universe in another profound way. In the distant past, the space between galaxies was filled with large amounts of neutral hydrogen gas. This neutral hydrogen absorbed energetic ultraviolet light very effectively, making the universe somewhat opaque to certain wavelengths of radiation. Over time, however, radiation from the first generations of stars and galaxies began to transform this environment. Energetic photons emitted by early stars could strip electrons away from hydrogen atoms, turning neutral hydrogen into ionized hydrogen. As more and more galaxies formed and began producing ultraviolet radiation, expanding bubbles of ionized gas spread outward through intergalactic space. Eventually, these bubbles overlapped, and much of the hydrogen between galaxies became ionized. This transition, known as cosmic reionization, marked a major turning point in the history of the universe. Once most intergalactic hydrogen became ionized, ultraviolet light could travel much more freely across cosmic distances. The universe effectively became more transparent, allowing radiation from distant galaxies to reach us with fewer obstacles. By studying the spectra of extremely distant galaxies and quasars, astronomers can search for signs of this transition and estimate when reionization occurred. Understanding this period is one of the most important goals of modern astronomy because it represents the moment when the first luminous structures transformed the universe from a dark, neutral environment into the transparent cosmos we observe today. In the next stage of our journey, we will explore how the newest generation of space telescopes is helping astronomers study galaxies from this remarkable era in even greater detail, revealing objects that formed only a few 100 million years after the beginning of cosmic time. In recent years, a new generation of space telescopes has begun exploring the distant universe with an extraordinary level of sensitivity. These instruments were designed specifically to detect the faint infrared glow of the earliest galaxies, allowing astronomers to peer farther back into cosmic history than ever before. With these telescopes, objects that once appeared as tiny unresolved dots are beginning to reveal shapes, structures, and even chemical details that were previously impossible to measure. One of the most important advantages of modern space telescopes is their ability to observe the universe above Earth's atmosphere. Our atmosphere absorbs large portions of infrared radiation and introduces subtle distortions into astronomical images. Even the best ground-based telescopes must constantly correct for the blurring effects of atmospheric turbulence. By placing telescopes in space, astronomers remove this obstacle entirely, allowing detectors to capture faint light with far greater clarity. As these telescopes began collecting deep infrared observations, astronomers started discovering galaxies that appear to have formed surprisingly early in the universe's history. Some of these galaxies may have existed only a few 100 million years after the first stars ignited. At such early times, the universe was still a relatively simple place. The first galaxies were assembling from streams of gas flowing along the dark matter filaments of the cosmic web. Yet, even within this young environment, certain galaxies seem to have grown rapidly, accumulating stars and structure faster than many earlier theories predicted. This has sparked lively discussions among astronomers. If galaxies formed so quickly after the beginning of cosmic history, it may mean that the processes governing star formation and gas collapse were more efficient than previously believed. Another possibility is that these galaxies are being magnified by gravitational lensing from foreground objects, making them appear larger and brighter than they truly are. Careful measurements are required to determine which explanation best fits the observations. To understand these distant galaxies more clearly, astronomers rely on spectroscopy. By spreading a galaxy's light into a spectrum, scientists can identify subtle fingerprints left by different atoms and molecules within the galaxy's gas. These spectral signatures reveal not only chemical composition but also motion. If gas inside a galaxy is rotating, expanding, or flowing inward, the spectral lines shift slightly in wavelength, allowing astronomers to measure these movements even across billions of light years. This information helps researchers determine whether early galaxies were already developing rotating disks, forming dense central regions, or experiencing powerful outflows driven by stellar winds and supernova explosions. In some cases, the spectra reveal the presence of ionized gas clouds extending far beyond the visible stars. These glowing regions may represent material flowing outward from intense star formation, or gas falling inward to fuel future generations of stars. At the same time, astronomers are refining their models of how galaxies evolve over time. Computer simulations play a crucial role in this effort. In these simulations, scientists recreate enormous volumes of the universe using equations that describe gravity, gas dynamics, radiation, and the behavior of dark matter. By allowing these virtual universes to evolve over billions of simulated years, researchers can compare the resulting galaxies with real observations. When simulations and observations match, it strengthens confidence in our understanding of cosmic processes. When they differ, it signals that something in the models may be incomplete or misunderstood. In this way, every surprising galaxy discovered in the distant universe becomes a valuable clue that helps improve our picture of cosmic history. As telescopes grow more powerful, astronomers are also beginning to resolve structures within these early galaxies. Instead of appearing as single blobs of light, some galaxies reveal multiple bright clumps where star formation is concentrated. Others show elongated shapes that may represent young rotating disks forming for the first time. These glimpses provide a rare opportunity to witness galaxies during their formative stages. Yet even with these technological advances, much of the early universe remains mysterious. Many galaxies are still too faint to study in detail, and the earliest generations of stars may have formed in environments that are extremely difficult to observe directly. Each improvement in telescope sensitivity opens new windows into these hidden epochs. In the next part of our journey, we will explore how astronomers combine observations across many wavelengths: radio, infrared, visible light, and X-rays, to build a complete picture of galaxy evolution. By stitching together these different perspectives, scientists are gradually revealing the layered story of how galaxies formed, grew, and shaped the universe we see today. To truly understand distant galaxies, astronomers rarely rely on a single type of observation. A galaxy is not made of stars alone. It is a complex system filled with gas, dust, magnetic fields, and sometimes powerful activity near its central black hole. Each of these components reveals itself most clearly in a different part of the electromagnetic spectrum. For this reason, astronomers study galaxies across many wavelengths of light, combining observations from multiple telescopes to reconstruct the full story of how these systems evolve. Visible light is often the most familiar view. When telescopes observe galaxies in visible wavelengths, they capture the combined glow of billions of stars. Spiral arms, glowing clusters, and bright star-forming regions become visible in these images. But visible light can only reveal part of what is happening inside a galaxy. Large amounts of star formation often occur inside thick clouds of gas and dust that block visible light almost completely. Infrared observations help solve this problem. When dust absorbs energetic radiation from young stars, it warms slightly and releases that energy again as infrared radiation. Infrared telescopes can detect this warm glow, allowing astronomers to discover regions of intense star formation that would otherwise remain hidden. In many distant galaxies, infrared observations reveal that enormous numbers of stars are forming behind curtains of dust, quietly shaping the galaxy from within. Radio telescopes add another important layer to this picture. Radio wavelengths are particularly useful for detecting cold gas, the raw material from which stars are formed. One of the most important signals comes from neutral hydrogen, the most abundant element in the universe. Hydrogen atoms naturally emit radio waves at a specific wavelength, allowing astronomers to map enormous reservoirs of gas inside galaxies. By observing this signal, scientists can see where the fuel for future star formation is stored and how that gas moves through the galaxy. Radio observations can also detect molecules such as carbon monoxide, which trace dense clouds where stars are actively forming. These measurements reveal how gas flows inward through galactic disks, sometimes feeding central star formation or fueling activity around a supermassive black hole. X-ray observations reveal yet another side of galaxies. Extremely hot gas, heated to millions of degrees, emits X-rays that can be detected by space telescopes designed for this energetic radiation. In galaxy clusters, this hot gas fills the space between galaxies and glows brightly in X-rays. Within individual galaxies, X-rays often originate from violent environments such as supernova remnants or the regions near actively feeding black holes. By combining observations from visible, infrared, radio, and X-ray wavelengths, astronomers create a layered view of galaxies that resembles a detailed map rather than a simple photograph. Each wavelength highlights a different physical process: star formation, gas flows, energetic explosions, or the quiet glow of aging stars. Together, these observations reveal how galaxies function as complex ecosystems evolving across cosmic time. This multi-wavelength approach has become especially important when studying distant galaxies. Light from the earliest galaxies has traveled for billions of years before reaching our telescopes. Along the way, it has been stretched, dimmed, and sometimes partially absorbed by gas and dust. Observing the same galaxy at several wavelengths helps astronomers separate these effects and uncover the galaxy's true nature. For example, a galaxy that appears faint in visible light might actually be undergoing a powerful burst of star formation hidden by thick dust clouds. Infrared observations would reveal the warm glow of that dust, while radio observations could show the cold gas feeding the process. Meanwhile, X-ray data might detect energetic activity from a growing black hole at the galaxy's center. When these different observations are combined, distant galaxies transform from simple points of light into rich scientific stories. Astronomers can measure how rapidly stars are forming, how gas is moving through the galaxy, and how central black holes may be influencing the surrounding environment. Each wavelength contributes a different voice to the cosmic narrative. And as technology continues improving, astronomers are building instruments capable of observing the universe with even greater precision. These new observatories will allow scientists to explore galaxies at earlier stages of cosmic history, revealing details that were once completely beyond our reach. In the final part of our journey, we will slowly step back from these scientific tools and reflect on the deeper perspective they provide. The distant galaxies we observe are not simply objects scattered across space. They are ancient messages carried by light across billions of years, offering us a quiet glimpse into the long unfolding story of the universe. As our journey through distant galaxies slowly comes to a quiet close, it is worth pausing for a moment to reflect on the extraordinary perspective that astronomy offers. Every distant galaxy we observe is more than a distant object floating somewhere in space. It is a message carried by light across vast stretches of time. When that light finally reaches our telescopes, it brings with it a snapshot of the universe as it once was, often billions of years in the past. Because light travels at a finite speed, no telescope can ever show us the universe exactly as it exists right now. Instead, the cosmos appears as a layered archive of history. Nearby galaxies show us the universe in relatively recent times. More distant galaxies reveal earlier chapters, when galaxies were still assembling and stars were forming in great abundance. And the faintest, most remote galaxies allow us to glimpse the era when the first structures were beginning to emerge from the young universe. In this sense, every astronomical observation becomes a kind of time travel. A single deep image of the sky can contain galaxies from many different ages of the universe at once. Some of the light in that image may have begun its journey a few million years ago. Other photons may have left their galaxies billions of years before the Earth even existed. All of those ancient messages arrive together in a brief moment when a telescope records them. It is also possible that some of the galaxies we observe today no longer exist in the same form. Over billions of years, galaxies can collide, merge, or transform dramatically. The galaxy whose ancient light reaches our instruments tonight may have already changed beyond recognition long ago. Yet the photons that left it during that earlier moment continue their journey unchanged, faithfully carrying the memory of what once was. This idea can feel both mysterious and beautiful. The night sky becomes a vast museum of cosmic history, where every point of light preserves a story from a different era. By studying these ancient signals carefully, astronomers can reconstruct the long evolution of the universe, from the earliest galaxies to the complex cosmic structures we see today. The journey of a single photon from a distant galaxy is almost unimaginable. After leaving its source, the photon travels across the expanding universe for billions of years. Along the way, it passes through the sparse gas that fills intergalactic space, sometimes slipping past galaxies and clusters that bend its path slightly through gravity. Eventually, after a journey longer than the entire history of human civilization, the photon arrives at Earth. When it finally reaches a telescope, the encounter is almost instantaneous. A detector records the photon in a fraction of a second, converting its energy into a tiny signal that astronomers can analyze. Yet that brief moment represents the end of a voyage that lasted longer than most structures on our planet have existed. Millions or even billions of such photons are collected during a deep observation. One by one, they build an image, a spectrum, or a measurement that allows astronomers to understand the galaxy that sent them. From these faint signals, scientists learn about the galaxy's stars, its gas, its motion, and its place within the cosmic web. What makes this process remarkable is that it relies entirely on information carried by light. We cannot travel to distant galaxies or examine them directly. Instead, we read the stories written in their photons. The colors of the light reveal chemical elements. Subtle shifts in wavelength reveal motion. Variations in brightness reveal structure and activity. In this way, light becomes the language through which the universe tells its story. As technology advances, our ability to read that language continues to improve. New telescopes will observe the sky with greater sensitivity, capturing even fainter galaxies from deeper in cosmic time. Future instruments may reveal the very first galaxies that formed after the birth of the universe, allowing astronomers to explore chapters of cosmic history that are still hidden from view today. Yet even with all these discoveries ahead, the quiet wonder of distant galaxies remains unchanged. Each one is a vast city of stars shining across unimaginable distances. Each one carries the memory of a different era in the universe's history. And together they remind us that our own galaxy, our own star, and even our own planet are part of a much larger cosmic story unfolding across billions of years. So as the night grows quiet and your thoughts begin to drift, imagine those distant galaxies continuing their slow, graceful journeys through space. Their light is still traveling, still crossing the silent depths of the universe, carrying ancient messages toward future observers who may one day look up and wonder about the same stars. And somewhere in that vast darkness, new galaxies are still forming, new stars are still igniting, and the universe continues its patient, endless unfolding.